NENOMATICA, where mathematics meets YouTube excellence. Welcome to our mathematical proof video. Today we'll be working on proving an inequality using algebraic techniques and careful reasoning. Let's start with our example. Here, we need to prove an inequality based on several given conditions. Our first condition is that x squared equals y squared plus c squared. Next, we're told that x, y, and z are all positive. And finally, we're given that lambda is greater than 2. We need to prove that x raised to the power of lambda is greater than y raised to the power of lambda plus c raised to the power of lambda. Let's begin our proof with a key step that will help us establish the inequality. We'll start by writing x to the power lambda minus y to the power lambda minus c to the power lambda, and rewrite it as x to the power lambda minus 2 multiplied by x squared minus y to the power lambda minus c to the power lambda. This is our first algebraic manipulation to work toward our goal. Now, we know from our given conditions that x squared equals y squared plus c squared, so we can substitute this into our equation. This gives us x to the power lambda minus y to the power lambda minus c to the power lambda equals x to the power lambda minus 2 multiplied by the quantity y squared plus c squared minus y to the power lambda minus c to the power lambda. In the next step, we'll distribute x to the power lambda minus 2. When we multiply it through the parentheses, we get y squared times x to the power lambda minus 2 plus c squared times x to the power lambda minus 2 minus y to the power lambda minus c to the power lambda. Next, we rearrange the terms to group similar expressions together. We'll rewrite this as y squared times x to the power lambda minus 2 minus y to the power lambda plus z squared times x to the power lambda minus 2 minus c to the power lambda. Now, we'll factor out y squared from the first group and z squared from the second group. This gives us y squared times the quantity x to the power lambda minus 2 minus y to the power lambda minus 2 plus c squared times the quantity x to the power lambda minus 2 minus c to the power lambda minus 2. We've labeled this as equation I, which we'll reference later. Let's analyze what we know about the expressions in the parentheses. First, we know that lambda minus 2 is greater than 0 since lambda is greater than 2. We also know that x is greater than y, because from x squared equals y squared plus c squared. And given that z is positive, we can deduce that x is greater than y. Therefore, x to the power lambda minus 2 is greater than y to the power lambda minus 2, which means x to the power lambda minus 2 minus y to the power lambda minus 2 is greater than 0. By the same logic, we can show that x is greater than z, and therefore x to the power lambda minus 2 minus c to the power lambda minus 2 is also greater than 0. Now, looking back at equation I, we have two positive terms on the right side, y squared times a positive number plus z squared times a positive number. This means that x to the power lambda minus y to the power lambda minus c to the power lambda is greater than 0, which we can rewrite as x to the power lambda is greater than y to the power lambda plus c to the power lambda. And that's exactly what we needed to prove. Let's summarize what we've learned from this proof. We started with the conditions that x squared equals y squared plus c squared. All variables are positive, and lambda is greater than 2. Through algebraic manipulation, we rewrote the inequality in terms of the difference between powers. We used our conditions to show that these differences are positive. And finally, we concluded that x to the power lambda is greater than y to the power lambda plus c to the power lambda. This proof demonstrates important techniques in inequality problems, including clever algebraic manipulation and substitution, factoring to isolate terms, and analyzing the signs of expressions to prove inequalities. Welcome to this mathematics video, where we'll be proving an interesting property about the sum of fractions. The problem states, prove that the sum of any selection of fractions from the sequence 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on, is always less than 1. Let's start by formalizing this problem. Suppose we have n fractions from this sequence, represented as 1 over a squared, 1 over b squared, and so on, up to 1 over l squared, where a, b, c, and so on are the denominators we've selected. We know that it is at least 2, b is at least 3, c is at least 4, and this pattern continues. More specifically, we can write that b is at least a plus 1, c is at least a plus 2, and so on, until L is at least a plus n minus 1. Now, we'll use an important inequality that we've previously proven. For any positive integer n and a positive integer p, the sum from k equals n plus 1 to n plus p of 1 over k squared is less than 1 over n minus 1 over n plus p. We can rearrange this to get 1 over n plus 1 plus 1 over n plus 2, and so on, up to 1 over n plus p is less than 1 over n minus 1 over n plus p. Let's apply this inequality to our problem. We can write that the sum of our selected fractions, which is 1 over squared plus 1 over b squared, and so on, up to 1 over l squared, is less than or equal to 1 over a squared plus 1 over a plus 1 squared, and so on, up to 1 over a plus n minus 1 squared. According to our key inequality, the right side of this equation is less than 1 over a minus 1 over a plus n minus 1. Let's continue with the next steps in our proof. From our previous inequality, we've established that 1 over a squared plus 1 over b squared, and so on, up to 1 over l squared, is less than 1 over a minus 1 over a plus n minus 1. Through algebraic manipulation, we can simplify the right side to get n over quantity a minus 1 times quantity a plus n minus 1. Now, we observe that a minus 1 is at least 1 because we know a is at least 2. Also, a plus n minus 1 is at least n because it is at least 1. Therefore, quantity a minus 1 times quantity a plus n minus 1 is at least n times 1, which is just n. Now, we're getting to the final steps of our proof. Since the denominator in our fraction is at least n, we have 1 over a squared plus 1 over b squared, and so on, up to 1 over l squared, is less than n over n, which equals 1. Therefore, we have proven that the sum of any selection of fractions from 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on, is always less than 1. Welcome to our math tutorial. Today, we're going to solve an inequality problem using trigonometric parameterization. Let's start with the following problem. If we have the conditions a squared plus b squared equals 1 and m squared plus n squared equals 1, prove that the absolute value of a m plus bn is less than or equal to 1. A squared plus b squared equals 1, it's clear that we can find an angle alpha such that it equals cosine alpha and b equals sine alpha. We can verify that a squared plus b squared equals cosine squared alpha plus sine squared alpha, which equals 1 by the Pythagorean identity. Similarly, for the second condition, m squared plus n squared equals 1, we can find another angle, let's call it alpha prime, such that m equals cosine alpha prime and n equals sine alpha prime. We verify that n squared plus m squared equals sine squared alpha prime plus cosine squared alpha prime, which also equals 1. Now, we substitute our parameterizations into the expression a m plus b n that we want to prove is less than or equal to 1 in absolute value. We get cosine alpha times cosine alpha prime plus sine alpha times sine alpha prime. This can be recognized as the cosine of the difference between alpha and alpha prime. Finally, we know that the absolute value of cosine of any angle is always less than or equal to 1. Therefore, the absolute value of a m plus bn, which equals the absolute value of cosine of alpha minus alpha prime, must be less than or equal to 1. This completes our proof. Welcome to this mathematics video. Today, we'll work through a step-by-step proof of an inequality involving 3 positive variables, a, b, and c. Let's follow the algorithm shown in the image. First, we establish 3 intermediate inequalities. The first inequality states that a squared is greater than or equal to a squared minus the quantity b minus c squared. The second inequality states that b squared is greater than or equal to b squared minus the quantity c minus a squared. And the third inequality states that c squared is greater than or equal to c squared minus the quantity a minus b squared. Now, following the algorithm, we multiply all 3 inequalities together. On the left side, we get a squared times b squared times c squared, which is a squared b squared c squared. On the right side, we get a squared minus the quantity b minus c squared, times b squared minus the quantity c minus a squared, times c squared minus the quantity a minus b squared. Following the algorithm, we'll now expand the right side of our inequality. Let's expand each factor. A A squared minus the quantity b minus c squared becomes a minus the quantity b minus c times a plus the quantity b minus c. Similarly, b squared minus the quantity c minus a squared becomes b minus the quantity c minus a times b plus the quantity c minus a. And c squared minus the quantity a minus b squared becomes c minus the quantity a minus b times c plus the quantity a minus b. Now, following the algorithm, we'll simplify each term in the expansion. The term a minus the quantity b minus c simplifies to a minus b plus c, which is a plus c minus b. The term a plus the quantity b minus c simplifies to a plus b minus c. The term b minus the quantity c minus a simplifies to b minus c plus a, which is b plus a minus c. The term b plus the quantity c minus a simplifies to b plus c minus a. The term c minus the quantity a minus b simplifies to c minus a plus b, which is c plus b minus a. And finally, the term c plus the quantity a minus b simplifies to c plus a minus b. Following the algorithm, we'll now regroup the terms. Notice that a plus c minus b appears twice, a plus b minus c appears twice, and b plus c minus a appears twice. So we can rewrite our inequality as a squared b squared c squared is greater than or equal to the product of a plus c minus b, a plus b minus c, and b plus c minus a, with each term squared. Finally, following the algorithm, we'll take the square root of both sides to complete our proof. Taking the square root of a squared b squared c squared gives us abc. Taking the square root of the right side, we get the product of a plus c minus b, a plus b minus c, and b plus c minus a. Therefore, we've proven that ABC is greater than or equal to the product of a plus b minus c, a plus c minus b, and b plus c minus a, which was our goal. Let's summarize what we've learned in this proof. We started with positive values a, b, and c that satisfy specific triangle inequality conditions. We established 3 intermediate inequalities involving squared terms. We multiplied these inequalities and used the difference of squares formula to expand. After simplifying and regrouping terms, we took the square root of both sides to prove that ABC is greater than or equal to the product of a plus b minus c, a plus c minus b, and b plus c minus a. This is an elegant application of algebraic manipulation and inequality properties. Today, we'll explore an interesting proof about the values of polynomial functions. We'll go through this proof step by step and make sure we understand the mathematical concepts involved. Let's start with the problem statement. Suppose we have integer numbers x sub 0, x sub 1, up to x sub n, such that x sub 0 is less than x sub 1 is less than x sub n. Prove that for any polynomial of degree n in the form x to the power of n plus a sub 1 times x to the power of n minus 1 plus a sub n at points x sub 0, x sub 1 through x sub n, this polynomial takes on values such that at least one of them is greater than or equal to n factorial divided by 2 to the power of n. Let's solve this step by step following the approach shown in the image. First, let's denote our polynomial function as f of x. We'll define a value m as the maximum of the absolute values of the function at our given points. So, m is the maximum of the absolute values of f of x sub 0, f of x sub 1, and so on, up to f of x sub n. The key insight in this proof is to establish a relationship between m and a specific expression. Let's look at the first inequality we need. 1 is less than or equal to m times the sum of 3 fractions. The first fraction is 1 divided by the product of x sub 0 minus x sub 1, x sub 0 minus x sub 2, and so on until x sub 0 minus x sub n. The second fraction is 1 divided by the product of x sub 1 minus x sub 0, x sub 1 minus x sub 2, and so on until x sub 1 minus x sub n. And we continue this pattern for all the points up to the last fraction, which is 1 divided by the product of x sub n minus x sub 0, x sub n minus x sub 1, and so on until x sub n minus x sub n minus 1. Now, according to the conditions of our problem, we can observe that the absolute value of x sub k minus x sub 0, x sub k minus x sub 1, and so on, skipping x sub k minus x sub k, until x sub k minus x sub n is greater than or equal to k factorial times n minus k factorial. This is because the integers are in ascending order, so each difference x sub k minus x sub j for j less than k is at least 1, And each difference x sub k minus x sub j for j greater than k is at least -1. From this, we can derive that 1 divided by the absolute value of the product of x sub k minus x sub 0, x sub k minus x sub 1, and so on until x sub k minus x sub n, where we remove the term x sub k minus x sub k, is less than or equal to 1 divided by k factorial times n minus k factorial. This gives us a useful bound for each of our fractions in the first inequality. Now comes the most interesting part. When we sum all these fractions and multiply by m, we can express it in a simplified form. M divided by n factorial times the sum from k equals 0 to n of n choose k equals m times 2 to the power of n divided by n factorial. This is because the sum of binomial coefficients n choose k from k equals 0 to n equals 2 to the power of n. Therefore, we get the inequality m times 2 to the power of n divided by n factorial is greater than or equal to 1. Rearranging, we get m is greater than or equal to n factorial divided by 2 to the power of n, which is exactly what we wanted to prove. Therefore, we have proven that for any polynomial of degree n in the form x to the n plus a sub 1x to the n minus 1 plus a sub n at points x sub 0, x sub 1 through x sub n, the polynomial takes values such that at least one of them has absolute value greater than or equal to n factorial divided by 2 to the n. This is a fascinating result about the behavior of polynomial functions at integer points. To summarize what we've learned, we proved that any polynomial of degree n, when evaluated at n plus 1 distinct integer points, will take at least one value with absolute value greater than or equal to n factorial divided by 2 to the n. This theorem has interesting implications in polynomial interpolation and approximation theory. It shows that polynomials must have relatively large values at some integer points. I hope you enjoyed this mathematical journey. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.